All right, guys, here we go for the second module. This is module 19 in chapter 6 on population community ecology. So we'll go ahead and get started. So chapter 6, module 19. After going through this one, we should be able to explain exponential growth models of populations, which produce something called a J-shaped curve. Describe how the logistic growth model incorporates a carrying capacity or a maximum amount of population and produces something called an S-shaped curve. Compare the reproductive strategies and survivorship curves of different species, and then explore and explain the dynamics that occur in something called metapopulations. All right, so the exponential growth model, which is what we're going to be talking about here, describes populations that continuously increase. Basically, there's nothing that could stop the increase of this population. It's not really realistic because all populations have a maximum number, but this is just assuming that it would grow over time. So population growth models, what are they? In order to understand this, we need to go over these terms. A population growth model is a mathematical equation that are different mathematical equations that can be used to predict population size at any moment in time. The population growth rate is going to be equal to the number of offspring an individual can produce over a given time minus the deaths of the individual or its offspring during the same period. So the population growth rate is equal to the births minus the deaths. All right. The intrinsic growth rate is going to be R. That's going to be the maximum potential for growth of a population under ideal conditions with unlimited resources. This means there'd be unlimited food, unlimited shelter, unlimited water, no factors, no predators, things like that. That's the intrinsic growth rate, the maximum growth rate. The exponential growth model is going to be an equation that you can see right here, all right? And it's a growth model that estimates a population's future size, NT. So NT is going to be, remember, big N from the previous chapter was population. That little T next to it is going to be time, so at a certain time. So T could be 30 years. So the population in 30 years based on this model would be equal to n sub 0, which is the number of individuals currently in the population is n sub 0, times e, the mathematical e that you guys all learned at some point, raised to the r times t power, where r is that intrinsic growth rate we just talked about, okay? And t is the period of time, which in that example I said would have been 30 years. So you would take that number, n sub 0, let's say there's 30 people in the population, you multiply that, so that'd be 30 times e, the mathematical constant e, to the r, which intrinsic growth rate might be 0.2 per year. And then t would be time 30. I know I picked 30 twice, it's just because I'm coming up with the top of my head. And then you would multiply that out and get your answer. And so what this will produce is this will produce a J-shaped curve that I'll show you on the next slide, just like this. It looks like a J. You see right there. Oh, wow. All right. And so that comes from this equation. The time versus the population size. The population will increase exponentially over time. This is called the exponential growth model. Again, this is what happens when populations are not limited by resources, and then this gives you very, very rapid population growth. More bursts occur with each step in time, creating this J-shaped growth curve. So the logistic growth model describes populations. Most of the populations on Earth, they experience something called a carrying capacity, which is going to be the maximum amount of population that can fit because there are limited resources. There is limited food. There is limited shelter, water, etc. There are predators, all right? So there's something called a limiting resource. Now, a limiting resource is a resource that a population cannot live without, and that occurs in quantities lower than the population required to increase in size exponentially. classic example, of course, is food. All right. The carrying capacity, which gives you this constant K, is the limit. That's how many individuals in a population that environment can sustain. You can't go above the K and survive. You can go above the K, but there's going to be a population die-off. So the logistic growth model is more realistic than the exponential growth model because it incorporates those limits, that K. So the logistic growth model is a growth model that describes a population whose growth is initially exponential but slows as the population approaches the carrying capacity of that environment. And this produces, instead of a J-shaped curve, this produces an S-shaped curve, and this is the shape of the logistic growth model when graphed. As you can see here, it gives you that S shape. So what you've got going on here, this line is your carrying capacity, K. All right. So what will happen is that your population will initially have exponential growth. All right. But as resources, as that population starts to eat, let's call it food, as it starts to eat the food that's in the area, the population will realize that there's not enough food for it to continue growing exponentially. So the growth will start to taper off, and you'll flatten out, and you'll have an increase in population, but there will be a time at which the population will basically flatten out and not grow anymore. And we're seeing this actually in human populations. As humans went through the Industrial Revolution, it looked like we were all going J, all right? We were going J, we were going straight up. But some stuff happened, all right, that causes definitely developed countries, MEDCs, to flatten out. And we'll talk about that more in the next chapter. All right. So the logistic growth model, if food becomes scarce or other conditions change, a population can experience fluctuations in the logistic growth model. It doesn't ever just fit that perfect S shape. We will overshoot. All right. So if a population becomes larger than the environment's carrying capacity, if it goes over that K line, what you're going to see is you're going to see an overshoot and a little bit of a die-off, which is a rapid decline in population due to death. All right. So species have different reproductive strategies and distinct survivorship curves. We have two types of species we like to talk about in here. K-selected species. And a K-selected species is going to have low intrinsic growth rate. So it's going to have a low growth rate that causes the population to increase slowly until it reaches its carrying capacity. So this would follow your S-shaped curve, all right? Your R-selected species, remember we talked about R being that exponential growth rate, right? So this is a species that has a high intrinsic growth rate, all right? Which often leads to population overshoots and die-offs. Not small ones, but these ones will go up and then crash down, all right? These usually have fast reproduction. All right, and you can see in here the difference between K-selected species and R-selected species. The lifespan of K-selected species is usually going to be long, and R-selected species would be short. So things like insects would be R-selected species, all right? K-selected species would be things like humans or large mammals, things like that. Time to reproductive maturity, it takes K-selected species relatively a lot longer to become reproductively mature than it does for R-selected species. K-selected species have very few number of reproductive events, whereas R-selected species are constantly. Number of offspring is many in the R-selected species, but very few comparatively in the K-selected species. The size of offspring is large. R-selected species is small. Parental care is usually present in K-selected species and absent in R-selected species. They're just born and then survive and adapt to their environment. Population growth rate is going to be slow for K-selected and fast for R-selected. Population regulation is going to be density dependent. All right, we talked about that before. So the population, the regulation, how many individuals are going to be there is going to depend on the conditions of that area, the food, the amount of land, and that's not going to be the case for R-selected species, which is why they end up having to die off. Population dynamics are near the carrying capacity and pretty stable for K-selected species after a time, and it's highly variable for R-selected species with lots of die-offs. So you can see K-selected species, like I said, larger animals, or even plants would be case-selected species. So like large trees, if you're thinking about a plant, giant redwoods, things like that, would be a case-selected species, along with like whales and humans and dolphins and tigers. And then our selected species are going to be things that reproduce very quickly, have very quick die-offs, can fill up a population and have a quick die-off, stuff like that. Like I said, insects, grasses, weeds, different things like that. All right, so a survivorship curve is a graph that represents the distinct patterns of a species' survival as a function of age. So these are graphs that describe, basically what's happening there, the species survival as a function of age. There are 3 types of survivorship curves. Type 1 survivorship curve is going to be a pattern of survival over time, whereas high survival throughout most of the lifespan, but individuals start to die in large numbers as they approach old age. This would be probably your K type species, okay? So humans, large animals like that. Type 2 survivorship curve are going to be a pattern of survival over time in which there's relatively constant decline in survivorship throughout most of the lifespan. So as species get older, more and more and more of them die, but it's pretty linear. That's a type 2. And type 3 are going to be like your R-selected species, where a pattern of survival over time, where there's low survival early in life with few individuals even reaching adulthood, would be a type 3. Here you can see the 3 types. You got type 1, you've got survivors on the y-axis and age on the x-axis. You see the type 1, you have a lot of survivors initially, and it only drops off as you reach old age. Type 2, the survivors constantly decline throughout. And type 3, you can see major drop off of young and barely any reach it to old age. So like I said, weeds, type 3. All right, type 1, with your case-selected species, they're going to be like whales, different mammals, things like that. And type 2, squirrels, rodents, different things like that are going to be your type 2 species. So interconnected populations from metapopulations. We have populations that these kind of influence their populations, how close they are to other populations. So there will be strips of natural habitat that connect different populations. So multiple populations that live in the same area, and there will be strips, these corridors of natural habitat that connect the populations. And then these lead to things called metapopulations. So these are spatially, so in space, they are distinct populations that are connected by occasional movements of individuals between them. And so this can cause a decline in population due to something called inbreeding depression. So this is when individuals with similar genotypes, typically relatives, but maybe not the same exact genotype, will reproduce with each other and produce offspring that have an impaired ability to survive and reproduce. So these are things that are genetically similar enough that they can produce offspring, but those offspring may not be viable because the species aren't similar enough, and that causes population depression. So you can see here, this is a cougar metapopulation. So you can see that cougars live in separate mountain ranges in New Mexico. Occasionally, however, individuals move between those mountain ranges. As you can see, there's spatially different mountain lions. Okay, they'll have different genetics because they have lived in those areas for a certain amount of times. Occasionally, individuals will move between the mountain ranges. All right, and will interbreed with the other populations. These movements can recolonize the mountain ranges with extinct populations and add individuals and genetic diversity to existing populations. So while sometimes it can produce a depression, other times like this, you can actually have this go if you know that that they're genetically similar enough that they're going to produce viable offspring. This can actually be encouraged by humans in order to increase diversity. And that's it for Module 19. Please let me know if you have any questions.